So welcome to the pre-recording of lecture 22 of MCS 320, Introduction to Symbolic Computation. And in this lecture, I will start out by making the distinction between symbolic and numeric differentiation. As an application of symbolic computation, we consider the problem of computing the tangent line at a point on a curve, which will involve implicit differentiation. So in the first part, using the slides, I hope to explain the main concepts. So here a problem from calculus. We have an expression which one can interpret as a sine function running at frequency 1, so the x can also be interpreted as time. The sine function of 2 pi times x makes one full cycle in the interval 0, 1, which can be interpreted as a time interval. But here we are interested in the value of the derivative of this expression at a point. And if we do this symbolically, as you have done many times in a calculus class, then this will be a two-step process. In the first step, you compute an expression for the derivative. In this case here, you apply the chain rule, first taking the derivative of sine and then multiplying with the derivative of the argument in the sine function. So that's the first step. In the second step, we take the value and we evaluate the expression for the derivative, here denoted by f prime. If there are, so observe here that this is an entirely symbolic calculation. Both steps are symbolic. The result is 2 times pi, and pi is a symbol, so it's an expression. So in general, if we have an expression which depends on a variable, then the symbolic differentiation will give us another expression for the derivative of the input expression with respect to the variable. Okay, that's symbolic differentiation, which produces expressions. Now, with numeric differentiation, there's just one simple step. Here we have given a function, so we must be able to evaluate of an expression. We have a value for the independent variable, so the function is here a function in one variable, and then we select the step size h, small, not too small, but certainly positive, and most commonly a recipe to approximate the derivative of the function at that point is by applying what is here written as the central difference formula. So this has the benefit that one does not, this is just a simple step process. The cost is twice evaluating the function, so if you can evaluate the function fast, then this will just go as fast as, almost as fast as evaluating the function, and it will give you directly a numerical result. The numerical result is an approximation. It depends on the value of h. If h is 10 to the power minus 2, then the error of the approximation will be about 10 to the power minus 4. that means about 3 to 4 decimal places. Now you are therefore tempted to take the h as small as possible. However, there is a threshold, a lower threshold on the step size, and that depends on the precision, the working precision, at which you can evaluate this function. So that's the first concern that is addressed by numerical analysis. And then there are also extrapolation methods. Another concern, another technique that can dramatically improve the accuracy at the expense of a little bit more function evaluations. Okay, so we will not address numerical differentiation in detail, although I will indicate how it is available in SciPy, a package that is offered in SageMath. An application of differentiation is here geometric. So here is the picture. We have the blue circle, so it's the unit circle. I picked a random point, so the random point is here, this dot. And then the green line is the tangent line of the tangent line at that point to the circle. So why is this special? Well, the circle x squared plus y squared minus 1 does not provide an explicit way of writing y in function of x. And that's one of the simplest cases for which we can illustrate implicit differentiation. So this is a technique that comes from calculus. What I do on this slide here is specifying the problem. So here is the question, the exercise that we will solve. Given an equation and a point, compute the slope of the tangent line to the curve defined by the equation and at the given point. So on the picture we had the blue circle, the red dot, and what we want to compute is the slope of that tangent line. But actually we can, once we have the slope, we can as well draw the tangent line as well. Now we can do this very systematically by viewing the y as a symbol y now as a function of x. So we are interested if we change x, what happens with y. So the tangent line is a very important approximation of the curve. So last lecture, at the end of last lecture, we worked with Newton's method. Here we are essentially doing something very similar. We are computing a tangent line. Also Newton's method, the geometric interpretation, is by computing a tangent line. Okay, so the first step is by seeing the problem differently. So we see now, here you see this equation. This becomes now an equation in which we apply the derivative operator. So we had the chain rule in the beginning. Well, here we apply the chain rule again. So we first take the derivative with respect to y, how in this equation we have the dependency with respect to y, but y depends on x. So we want to understand how at a point when we change x, what happens to y. Then we solve the equation for the derivative. So that's, we can do this. So both steps 2 and 3 have meaning because y is not an independent variable now, but is seen as something that depends on x. So we solve for the derivative, so that will give us an expression in x and y, and then we substitute the coordinates a and b for the point on the curve. So that's the main exercise that we will solve today. So the course is advancing. We are somewhere in the middle of the course. You can kind of see that we apply symbolic methods to obtain geometric visualizations. So in some sense, this is a geometry problem. Okay, so let me move to the hands-on practical part and swap the slides for the Jupyter notebook. So I have a Jupyter notebook prepared, and in case I blank out, I will swap to the prepared notebook, but let me build up the notebook step by step. So in this lecture we consider symbolic. So this is lecture 22 of the 8-week summer session. So we consider symbolic, numeric, and implicit differentiation. So this is the notebook that I'm using for my recording. Let's start with looking at symbolic differentiation. Remember the two-step process, so let me formulate the calculus problem. So compute the value of the derivative of the expression at x equals 1. So the variable x is by default defined, but let me define it anyway. So I will work then with expressions. So 2 times pi times x. So this is an expression which depends on x. So I can compute the derivative, so call it f1. I can do this by applying the function. So you see that in case you are a bit fuzzy on the mechanics of the chain rule, Sage does this for you automatically. And then the value of the derivative is then by replacing x by 1. So this gives us the symbolic result indeed. So it is an expression 2 times pi. Suppose I want the higher order derivative. Suppose I want the 5th order. Then I can do this in two ways. I can do diff fx, and then I have an extra parameter with the order. And you see that I've done this 5 times the chain rule, or SageMath has done it 5 times. I can do this alternatively. Diff is also a method. So diff is a function that works on expressions, but it's also method that works on the expressions. So speaking of functions, so let us look at a function which represents a polynomial with rational coefficients in 2 variables x and y. So let us first make, so we first will make a random polynomial. So this is already the third part, but we shouldn't forget what we learned in the first part of the course. So I will define a polynomial ring capital P, so with coefficients over the rationals. Doing this makes that I can generate a random element, say degree equals 5 and with 8 terms. So this gives me a polynomial, but I want to have a function, a proper SageMath function. So in order to do that, I need to convert this into an expression. So let me remind you that Q is not really an expression. You see that the singular comes in there, so it's belonging, it's not an expression. I cannot immediately use this. So to view Q as a function, a SageMath function, we must convert to an expression. So we have defined a polynomial ring, but I want to have a general ring where I'm going to use x and y as the variables. So I'm going to convert this into the symbolic ring. So I'm going to use x and y. On Q, I'm going to convert and substitute x by x and y by y. So that looks rather strange. So let me explain. So there are two x's and there are two y's, two different x and two different y's. So we have the x and the y, so it's still visible here at the very top. In my polynomial ring, I have declared x and y to be the variables of the polynomial. In the input cell 9, I defined x and y as the formal parameters of the function f. So they are defined at the left. So I'm using twice the x and the y. In input cell 7, anything that would be typed in x and y would automatically be considered as a polynomial with rational coefficients. In input cell 9, the x and the y are the formal parameters, and they appear at the right in the substitution. So in the symbolic ring, I'm going to replace the x and the y by the formal parameters x and y of the function. Why do we do all that? Well, it pays off. I can now take the derivative, and here I have only two variables, but I can take the derivative as a method applied to the function without specifying any variables. And you see what I obtain. Observe very carefully that what I get, observe that g is a function which returns a tuple. So what is in the tuple are the two partial derivatives. You can kind of see it a little bit first. So we have the first monomial is x to the power 4 times y. With respect to x, this becomes x to the power 3 times y. With respect to y, the y disappears from the monomial x to the power 4 times y. So what is this? So I used g. We computed the gradient of f. So the gradient is very important if you would be looking for extremal values of this expression f. In optimization, the gradient is computed all the time. We can still continue this. I can, at the same fashion, I can take the derivative from the gradient. And you see then that the type of h is now different. What I have is now a matrix of functions. So the derivative of the gradient is a matrix. It is the Hessian of the original expression in several variables. So the Hessian says something about the curvature of the function. Okay, so this is a very brief overview of the derivatives. Notice the symbolic nature. We start with expressions, we end up with expressions. So symbolic differentiation computes expressions. Let me now very briefly indicate numerical differentiation. And let us look exactly at the same problem, but now I will say approximate the derivative of the function. I will write explicitly more this with the notation of functions at x equals 1. Okay, in the slides I indicated the central difference formula. So this is what is used in the SciPy derivative. So I will import the derivative from the miscellaneous module from SciPy, and I will import this as the function numdiff. So it is important that this is a numerical function. So I have to define now a function f that is numerical. So we have done this already when we discovered vectorization with NumPy. So I will import NumPy because I want the sine function that is numerical. Also, I want the pi that is numerical. So my function that I will differentiate, I will define it as a Python function. It will apply the sine function of NumPy and also the NumPy pi. So this has to be an entirely numerical function, otherwise I will again end up with a symbolic result. If I would not replace pi by the numpy.pi, then my result would still contain this numpy. So I should say at this point I've practiced this, so I have prepared, but it would be good if you would do the help from numdiff. So it will give you the derivative of a function at the point x0. Then the step size is already 1 by default. So there are 2 parameters that you must specify. So let us try to do this. So I will do numdiff I have my function capital F. The point that I'm interested in is 1, and let me not provide any other different values. And you see that the dx is a little bit too large because I'm not believing it. So let me put the dx as 10 to the power minus 4. Why was I not believing this? Well, I remember our symbolic exercise. So the exact value is 2 times pi. So I will use the pi from numpy. So you can see that this is my first numerical approximation. I can also take this a little bit better, make this better by using 10 to the power minus 6. And then I can still increase the order that more points will be taken. Okay, so this is a brief excursion into numerical techniques. So they have the advantage of being much more direct, so there is no two-step process. But on the other hand, there are a lot more parameters and options to consider. Implicit differentiation. So let us now come to the main exercise for this session. So perhaps I can briefly flash up again what I want to do. So here is the slide that is still there. So I have a curve. Here I will take the unit circle. I have a random point on that curve, so the red dot, and I want to compute the tangent line to that through that point to the curve. And in particular the slope. So at that point, if we change x, then the y value will go down. So you can see geometrically, you can interpret the numbers what come out. So if what has happened thus far is too numerical or too algebraic, or then here it becomes more concrete. What is it actually that we are computing by derivatives? So we are computing a rate of change, a slope. You can also consider the green line a local approximation for the curve. So we have this round curve locally, and we experience that all the time. We are all living on some ball, but the earth looks flat enough to us if you walk around. Okay, go back through so I'm going to make this picture with SageMath. So I'm going to formulate the problem. Take a random point on the unit circle and construct the tangent line through that random point. So I will try to do this geometrically as well. So let me start with the definition of the unit circle. So that's the equation. I will call it circle. So x squared plus y squared minus 1 equals 0. So that's the algebraic definition of the circle. And I can plot this via the implicit plot. So I have two variables. I have to give the range for x and for y. And I don't like that when the circle shows up as an ellipse, so I will ask Sage to use the same aspect ratio for both the x and the y direction. So this is my command, so perhaps I can make this a little bit, so this is the plotting of the circle. So this is an object that we can render, so we can build up expressions one at a time. Our plots can also be constructed incrementally. So here you see a plot of the unit circle. And perhaps I could have decreased the size a little bit. Okay, so it's not an allowed option apparently, and it's not an option of the plot, might be an option of the show function, and it is not. Okay, it is. So now I have a tiny circle, so I can make it as big as I like, but I think the point is not that there is a circle. The point is that how do you plot this? That's the first curve, the first ingredient. The first input, we have a curve. Now our random point, but at this point in time we can actually start with the implicit differentiation. So I can, before I start with the point, I can start the symbolic calculation. So remember, so it's important enough, so the first step in the implicit differentiation is to view y as a function of x. So, and that's important. If you don't get this, then the entire exercise cannot be completed. If I would take the derivative now, then y is seen as independent of x. In some sense, I should have pointed this out in the plot as well. In the plot, I gave independently ranges for x and y. So that's important. So how do I do this? I will go through a new variable. I will call this capital Y. And y is a function of x. So the capital Y is actually also an expression. But what's the point? I can take the derivative of the capital Y with respect to x. You see, these are kind of these things that are very important to check. We can now work with the derivative of this function. So the y is only declared as a function of x. Nothing else is known about the y, the capital Y, but the fact that it depends on x means that its derivative is not 0. So if I would do the derivative of the little y with respect to x, which I will not do, but that would be 0, so that would not help us. Okay, I will now have a new circle where I will replace the little y with the capital Y. So you see that when I ask for to see the expression, it has indeed changed. So that is done step 1. So step 1 is now complete. So the first step is complete. we see that the second variable, now it is the capital Y, depends on x. So we can start do the second step and take the derivative with respect the derivative of y circle with respect to x. Derivative of the circle dc diff y circle with respect to x. And now you see it's still there on top in the output cell 29. You see that what appears is the derivative of y with respect to x. And that's actually the symbolic representation of the slope of the tangent line. Now it doesn't look so useful yet, but now comes the third step. In the third step we solve. So we started by deriving an equation. In the third step we solve the derived equation for the derivative of y with respect to x. Now you can do this by hand, but we don't do much computations by hand here, so we are asking Sage to solve for dy, and I will store this in the variable solve. And here you see that what Sage returns is a list of an equation where the left hand side is what I have solved for, the right hand side is the value of the slope. So I can get that out there. So the slope, or the expression for the slope, is the first component of the list, and the first component of the list is an equation, so I have to select the right hand side. And this is the symbolic answer to the question: compute an expression for the slope. And you see that this slope is not defined everywhere. If the denominator is 0, and you can see that happening, that's why we take a random point, but we will have a vertical asymptote at the endpoints of our circle. Okay, so now it's time for our numerical input. So we generate a random point on the circle and a random point on the unit circle. For that we can use the polar representation. So we have seen polar coordinates of complex numbers. So we have the cosine and the sine of t for some random angle t in the interval minus pi plus pi. So there are other ways how to pick points, but a very good way is by generating an angle, a random number, because actually I want to avoid the situations where y equals 0. So if I pick a random element from the RR, I will always get a number between -1 and 1. So that's why I will multiply with the numerical approximation for pi. So here now I have a positive number. It will be interesting. Our solution will be completely general. For random numbers, we will exclude the bad cases. So you can see many tangent lines. They will all work out. So, but this is a symbolic exercise. We have covert substitution. I'm not yet there with my point. So I have to take the cosine of the angle and the sine of the angle, and that gives me the two coordinates for the point. And what I'm going to do with these two coordinates, I'm going to replace in the slope. So I have here the expression for the slope. The x will be replaced by 0.9, and the y of x will be replaced by 0.39, will be replaced by b. So we defined simultaneous and sequential substitution. So this is a case where you may want to use sequential substitution. So the value for the slope is obtained by taking the expression for the slope and replacing. I'm first going to replace the most difficult part. So the y of x, I'm going to replace this by b, and then I'm going to replace the x by a. So here I'm using the more general syntax. You could do this in 2 steps as well. And that gives us the value for the slope. Note that the order of the substitution is important. You can also do it differently, but when you replace x by a, you won't have any more the y of x. So you will actually have the y of this 0.9. Okay, so my slope is negative, so that means that I will have a downward equation. Let me try to interpret it now. So I have the plot of the point. So there is the point that I can use with the coordinates a and b. So I'm going to make it a red point. And in order to see this, the size should be significant. So I'm going to show the plot of the circle and add to it the plot of the point. And here you see the plot. The slope is negative, so you can already imagine the tangent line. And indeed, that goes negative. So this is already an indication that the sign of the value of the slope is correct. Lastly, let me now make the drawing for the tangent line. So the equation for the tangent line is y minus b equals, but I will do minus the value of the slope times x minus a. So perhaps if your calculus is a little bit off, it's a long time ago that you did these problems. So let me document this. So the equation of a line with through the point AB and with slope m is, so let me, y minus b equals m times x minus a. So that is the property that I'm using, what you most likely still remember or should remember. You can verify when x equals a,
the right hand side is 0, and then in order for the left hand side to be 0, y has to be equal to b. So the slope is rise over run. If you put the x minus a to the left side, you have y minus b over x minus a. So that's another way to verify this. I will define an equation very similar like what we had with the circle. So I will plot all points for which this equation equals 0. So there are definitely better ways, more faster ways to plot this. But since I'm already using implicit plot for the circle, I'm going to make a plot of the line with the line command, where the implicit plot. It is indeed a line command. That's not what we are using here. So I have my expression, which is the tangent, and I will use the same range as I did for the circle. A line is a very special curve, and I will use green for the tangent line. Now, the final plot is obtained by adding the plot of the circle, the plot of the point, and the plot of the line. And here we go. So this is the final result. So this exercise is thereby solved. So this gives us a geometric verification of our symbolic calculations. And if you have executed this, then most likely your point was somewhere else, but whatever it was, it should have been on the circle. In the green line should also have passed and touched the blue curve as it does here. Okay, so this is the middle of the course, and I hope that you start to appreciate a little bit what we can do with symbolic computation. So we have the convenience of no longer have to worry about the specific derivative rules, but we can focus more on the actual understanding of the problems that we are trying to solve. So I hope this was interesting. I stop the recording now.